Hello there, and welcome to the Sleepy Science channel. I'm so glad you found your way here tonight. Maybe you've been thinking about the universe, about the invisible force that holds everything together. Or maybe you just need something gentle to carry you towards sleep. Either way, you're exactly where you need to be. Tonight, we're exploring gravity. Not with equations or complicated physics, but with wonder. We'll drift through the quiet pull that keeps your feet on the ground, the moon in the sky, and galaxies spinning in the dark. Some facts may surprise you. Others might settle over you like a soft blanket, warm and reassuring. And if this peaceful journey helps you rest, consider liking and subscribing. It helps others find their way here too. Also, I'd love to know where you're tuning from and what time it is there. It's fascinating to see how these videos connect people from around the world. For now, let yourself sink into comfort. Let your shoulders drop, your breathing slow, and your mind grow still. Because tonight, we're falling gently into the mystery of gravity itself. Gravity is the weakest of all fundamental forces. In the vast catalogue of forces that govern the universe, gravity holds a curious position. It's the weakest, by far. When you pick up a paperclip with a small magnet, that tiny piece of metal is overpowering the gravitational pull of the entire Earth. The electromagnetic force is stronger by a factor of about a trillion. And yet, gravity shapes galaxies, bends starlight, and holds the cosmos together. It wins not through strength, but through patience. Gravity never stops. It never turns off. It reaches across infinite distance, growing weaker, but never disappearing entirely. While other forces operate at the scale of atoms or particles, gravity operates on the scale of everything. Quiet, persistent, and endlessly patient, it pulls the universe into shape, one soft tug at a time. You are slightly lighter at the equator than at the poles. The Earth is not a perfect sphere. It bulges slightly at the equator due to its rotation, making the equator about 21 kilometers farther from the center of the Earth than the poles. And because gravity weakens with distance, you weigh just a little bit less standing at the equator than you would at the North or South Pole. The difference is small, less than 0.5%, but it's real. Add to that the centrifugal effect of Earth's spin, which pushes outward more strongly at the equator, and the effect becomes even more noticeable. So if you've ever wanted to feel lighter, take a trip to Ecuador or Kenya. Gravity will ease its grip ever so slightly, not because you've changed, but because the planet beneath you has a different shape. Even the ground you stand on shifts the weight you carry. Gravity isn't a force, it's the shape of space-time. For centuries, we thought gravity was a force, an invisible pull between masses. But Einstein revealed something far stranger. Gravity, he said, is not a force at all. It's geometry. Mass bends the fabric of space-time, the four-dimensional blend of space and time that makes up reality. When you drop a ball, it's not being pulled downward by some mysterious force. It's following the curved path that Earth's mass creates in space-time. Imagine a trampoline with a bowling ball in the center. The fabric dips. A marble placed nearby will roll toward the ball, not because it's pulled, but because the surface itself is curved. That's gravity. The universe isn't flat. It's warped by every star, planet, and particle, and we move through that warping, tracing invisible grooves in the shape of space itself. You create your own gravitational field. Right now, as you lie still, you are pulling on everything around you. Not much, but measurably. Your body has mass, and all mass creates gravity. You pull on the walls, the ceiling, the air, and even the distant stars, though your influence is vanishingly small. At the same time, everything pulls on you. The earth pulls strongest, of course, which is why you stay grounded. But the sun pulls too. So does the moon, Jupiter, and the Andromeda galaxy. Every atom in the universe is connected to every other atom through this gentle, invisible web. You are not separate from the cosmos. You are part of its gravitational conversation, a quiet participant in the endless exchange of influence that holds all things together. Even in stillness, you are reaching out and being reached for in return. Time moves slower in stronger gravity. Here's a truth that feels like fiction. Time is not constant. It flows at different rates depending on where you are and how strong gravity is around you. In strong gravitational fields, like near a massive planet or star, time moves more slowly compared to regions where gravity is weaker. This isn't philosophy, it's physics, confirmed by atomic clocks on airplanes and satellites. A clock on the ground floor of a building ticks slightly slower than one on the top floor because it's deeper in Earth's gravitational well. The difference is tiny, but it's real. If you stood near a black hole, time would crawl compared to someone far away in empty space. They might age years while you experience only minutes. Gravity doesn't just pull on objects, it pulls on time itself, stretching seconds into stillness. Gravity travels at the speed of light. If the sun suddenly disappeared, we wouldn't know it immediately. We'd still see its light for about 8 minutes, the time it takes for light to travel from the sun to Earth. But here's the twist. We'd also still feel its gravitational pull for those same 8 minutes. That's because gravity, like light, travels at a finite speed. Gravitational influence propagates through space-time as ripples, moving at exactly the speed of light. When massive objects accelerate or collide, they send out gravitational waves, disturbances in the fabric of space that race outward in all directions. These waves were predicted by Einstein and finally detected in 2015. A faint whisper from two colliding black holes over 1 billion light-years away. Gravity is not instant. It flows, it ripples, and it takes time to reach across the dark. You weigh less on a mountain. The higher you climb, the farther you are from the center of the Earth, and the weaker gravity becomes. It's not a dramatic change, but it's there. At sea level, gravity pulls with a certain strength. At the top of Mount Everest, about 18,800 meters up, you'd weigh roughly 0.5% less. The difference comes from two things. First, you're farther from Earth's mass. Second, there's less mass beneath you. Mountains, despite their size, don't add enough gravitational pull to compensate for the increased distance. So when you stand at a peak, looking out over clouds and valleys, you're not just closer to the sky, you're also a little bit freer. Gravity's grip loosens just slightly. At the edges of the world, gravity holds the moon in orbit, but the moon is drifting away. The moon doesn't fall into the Earth, and it doesn't fly off into space. It's caught in a delicate balance, constantly falling toward us, while also moving sideways fast enough to keep missing. That's what an orbit is, an endless fall. But the story doesn't end there. The moon is slowly drifting away from Earth, about 3.8 centimeters per year. The cause is tidal friction. As the moon pulls on Earth's oceans, creating tides, it also transfers energy. That energy gradually pushes the moon into a higher orbit. Billions of years ago, the moon was much closer, looming larger in the sky. And billions of years from now, it will be farther still, smaller and more distant. Gravity holds the moon close, but time pulls it away. A slow goodbye, measured in millimeters, across the span of ages. Gravity makes stars shine. At the heart of every star is a battle. Gravity pulls inward, trying to collapse the star into a single point. But deep in the core, nuclear fusion pushes outward, releasing energy as hydrogen atoms fuse into helium. These two forces, compression and expansion, balance perfectly for most of a star's life. Without gravity, fusion wouldn't happen. It's the crushing weight of a star's own mass that heats the core to millions of degrees, igniting the reactions that produce light. Every sunrise you've ever seen, every ray of warmth from the sun, is the result of gravity squeezing atoms so tightly they merge and glow. Stars don't just burn, they're held in place by their own weight, shining because gravity refuses to let them rest. Black holes are gravity taken to the extreme. In most of the universe, gravity is gentle, but in a black hole, it becomes absolute. A black hole forms when a massive star collapses under its own weight, compressing so much mass into such a small space that the gravitational pull becomes inescapable. Not even light can break free. That's why they're black. The boundary around a black hole is called the event horizon. Cross it, and there's no turning back. Space itself is so warped that all paths lead inward. Time behaves strangely there, slowing to a crawl from an outside perspective. And at the center lies the singularity, a point where gravity becomes infinite and the laws of physics as we know them break down. Black holes are not empty voids. They are gravity's final word, a place where the universe folds in on itself and goes silent. You experience microgravity when you're in free-fall. Astronauts aboard the International Space Station float as if there's no gravity, but that's not quite true. Gravity at that altitude is only about 10% weaker than on Earth's surface. So why do they float? Because they're in free fall. The ISS is constantly falling toward Earth, but it's also moving sideways so fast that it keeps missing the planet. Everything inside the station, astronauts, equipment, water, is falling at the same rate. Since there's no surface pushing back, they feel weightless. It's the same sensation you'd experience in an elevator if the cable snapped, though much more pleasant and longer lasting. Microgravity isn't the absence of gravity. It's the experience of surrendering to it completely, falling endlessly without ever hitting the ground. Gravity varies slightly across Earth's surface. Earth's gravity isn't uniform. Some places pull harder than others. Variations come from differences in altitude, the density of underlying rock, and even the distribution of mountains and ocean trenches. Scientists measure these tiny differences using satellites, creating maps of Earth's gravitational field. These maps reveal hidden features, underground water reserves, mineral deposits, and the shape of tectonic plates. The differences are subtle, far too small for you to feel, but they're real. Gravity is not a constant blanket. It's textured, shaped by the planet's inner workings and surface features. Even standing still, the pull you feel is unique to where you are. A fingerprint of place written in the language of mass and distance. The Sun's gravity reaches far beyond Pluto. When we think of the solar system, we often picture the 8 planets orbiting the Sun. But the Sun's gravitational influence extends much, much farther. Beyond Neptune, beyond Pluto, lies the Kuiper Belt, a region of icy bodies still bound to the Sun. And even farther out, about a light year away, is the Oort cloud, a vast shell of comets loosely held by the Sun's gravity. These objects take thousands of years to complete a single orbit. Some are barely moving, drifting at the very edge of the Sun's reach. The solar system doesn't have a sharp boundary. It fades slowly into interstellar space, a gradient of influence that stretches into the dark. Gravity is patient. Even at the fringes, where its pull is barely a whisper, it still holds on. Tides are caused by the moon's gravity twice a day. The ocean rises and falls, a rhythm as old as the moon itself. Tides are caused by gravity, specifically the moon's pull on Earth's water. The side of Earth facing the moon feels a slightly stronger pull than the center of the planet, causing water to bulge outward. On the opposite side, water also bulges because it's farther from the moon and feels less pull. As Earth rotates beneath these bulges, coastlines experience high and low tides. The Sun contributes too, though its effect is smaller. When the Sun and Moon align during new and full moons, their pulls combine, creating especially high and low tides called spring tides. Gravity, invisible and silent, moves entire oceans. The moon tugs and the seas answer. Gravity causes spaghettification near black holes. As you approach a black hole, gravity doesn't just pull on you, it stretches you. The difference in gravitational strength between your head and your feet becomes extreme. If you fell feet first, your feet would be pulled harder than your head, elongating your body like a piece of spaghetti. This process, charmingly called spaghettification or the tidal effect, would eventually tear you apart. For smaller black holes, this happens long before you reach the event horizon. For supermassive black holes, which have gentler gradients, you might cross the horizon intact, only to be stretched later. Either way, gravity doesn't just crush, it pulls unevenly, reshaping anything that ventures too close. In the grip of a black hole, even matter loses its form. Ancient people thought heavy objects fell faster. For thousands of years, it seemed obvious. A rock falls faster than a feather. So people, including the philosopher Aristotle, believed that heavier objects naturally fall more quickly. It made intuitive sense, but it was wrong. In the late 1500s, Galileo challenged this idea. Whether he actually dropped objects from the Leaning Tower of Pisa is debated, but his experiments showed that in the absence of air resistance, all objects fall at the same rate regardless of mass. A hammer and a feather released together in a vacuum hit the ground at the same time. This was later confirmed on the moon by Apollo 15 astronaut David Scott, who dropped both in the airless lunar environment. Gravity doesn't care how much you weigh. It accelerates everything equally. The only difference is the air pushing back. Gravity assists help spacecraft travel farther. When a spacecraft needs to reach distant planets, it doesn't always carry enough fuel to get there on its own. Instead, mission planners use gravity assists, also called slingshot maneuvers. The spacecraft flies close to a planet, entering its gravitational field. As it swings around, it steals a tiny bit of the planet's orbital momentum, speeding up without burning fuel. The planet slows down infinitesimally, though the effect is far too small to notice. Voyager 2 used gravity assists from Jupiter, Saturn, Uranus, and Neptune to tour the outer solar system. The technique turns gravity into a tool, a free boost from the planets themselves. In the silence of space, gravity becomes a helpful hand, pushing travelers farther than they could ever go alone. You're falling right now, and the ground is pushing back. It feels like you're lying still, but in truth, you're in a gravitational field. Earth's mass curves space-time around you, and you're trying to follow that curve, which means falling toward the center of the planet. But the ground is in the way. It pushes up on you with a force we call the normal force, preventing you from continuing your fall. This push is what you feel as weight. In a very real sense, you're not resting. You're being held up, constantly supported against the pull of gravity. If the ground suddenly vanished, you'd begin to fall. And in that moment of free fall, you'd feel weightless. Gravity never stops pulling. It's the surfaces beneath us, the floors, the chairs, the earth, that keep us from answering its call. Gravitational lensing lets us see distant galaxies. Light travels in straight lines, or so it seems. But when light passes near a massive object like a galaxy cluster, the object's gravity bends space-time, and the light follows that curve. This is called gravitational lensing. From our perspective, distant galaxies behind the cluster appear stretched, magnified, or even multiplied into arcs and rings. Einstein predicted this, and it was first observed during a solar eclipse in 1919, when stars near the Sun appeared shifted from their usual positions. Today, astronomers use gravitational lensing as a natural telescope, allowing us to see galaxies that would otherwise be too faint or distant. Gravity doesn't just pull on matter, it bends light itself, turning the universe into a lens, revealing what was hidden in the deep and distant dark. Your weight changes depending on where you are in the universe. Weight is not a fixed property. It's the measure of gravity's pull on your mass. On Earth, you might weigh 70 kilograms. On the Moon, where gravity is about 1/6 as strong, you'd weigh only 12 kilograms. On Jupiter, with its immense mass, you'd weigh over 160 kilograms. And in deep space, far from any star or planet, you'd weigh nothing at all, though your mass would remain the same. Weight is a relationship, a conversation between you and the nearest massive object. It changes with location, with distance, with the shape of the world beneath you. Mass is who you are. Weight is how the universe holds you. Gravitational waves were predicted a century before they were found. In 1915, Einstein's general relativity predicted that accelerating masses should produce ripples in space-time, like waves on a pond. But these gravitational waves would be incredibly faint, far too weak to detect with the technology of the time. For decades, they remained theoretical, a beautiful idea with no proof. Then, on September 14, 2015, 2 detectors in the United States picked up a signal. It lasted less than a second, a faint vibration in space-time caused by 2 black holes colliding over 1 billion light-years away. The discovery confirmed Einstein's prediction and opened a new way of observing the universe. We can now listen to gravity itself, hear the echoes of cosmic events that produce no light. A whisper from the fabric of reality finally heard. Planets don't orbit the Sun, they orbit a common center of mass. We say planets orbit the Sun, and that's mostly true. But technically, both the planet and the Sun orbit a point called the barycenter. the center of mass of the system. For small planets like Earth, the barycenter is so close to the Sun's center that the difference is negligible. But for Jupiter, the most massive planet, the barycenter lies just outside the Sun's surface, so the Sun actually wobbles slightly as Jupiter pulls on it. This same principle applies to binary star systems, where two stars orbit a point between them. Nothing in space sits perfectly still. Everything dances, pulled by everything else, tracing invisible circles around shared points of balance. Gravity is not a one-way pull, it's a mutual embrace. You can't feel gravity, only the resistance to it. This may sound strange, but you never actually feel gravity. What you feel is the ground, the chair, the floor pushing up against you. In free fall, like on a roller coaster drop or in orbit, you feel weightless because there's nothing pushing back. Gravity is still there, pulling just as strongly, but without resistance, you don't sense it. Your body has no gravity sensor. It can only detect force, contact, pressure. Gravity itself is silent and unfelt. It's only when something prevents your fall that you become aware of it. So when you feel heavy, you're not feeling gravity. You're feeling the world holding you up, resisting the pull, keeping you from the endless fall that gravity invites. Escape velocity depends on mass and radius. Every celestial body has an escape velocity, the speed needed to break free from its gravitational pull without further propulsion. For Earth, it's about 11.2 kilometers per second. For the Moon, it's much lower, about 2.4 kilometers per second. For the Sun, it's over 600 kilometers per second. Escape velocity depends on two things: the object's mass and its radius. A denser, more massive object requires a higher speed to escape. For a black hole, escape velocity exceeds the speed of light, which is why nothing, not even light, can leave. Escape velocity isn't about how high you go. It's about how fast you're moving when you leave. Go fast enough, and gravity's grip loosens. Go even faster, and you're free. Gravity makes time dilation measurable even on Earth. You don't need to visit a black hole to experience time dilation. It happens right here on Earth, though the effect is tiny. Atomic clocks, precise enough to measure billionths of a second, have been placed at different altitudes. The clock at higher elevation, where gravity is slightly weaker, ticks faster than the one closer to the ground. The difference is minuscule but real. GPS satellites experience this effect constantly. They orbit high above Earth where time flows faster. If engineers didn't account for this, GPS coordinates would drift by kilometers within a single day. Gravity doesn't just shape space, it shapes time. And even standing still, you're moving through time at a rate determined by how deep you sit in Earth's gravitational well. Gravity causes stars to collapse into neutron stars. When a massive star exhausts its fuel, fusion stops. Without the outward pressure to balance gravity's inward pull, the core collapses. If the star is massive enough, the collapse is catastrophic. Electrons are forced into protons, creating neutrons and releasing a flood of energy in a supernova explosion. What remains is a neutron star, an object about 20 kilometers across, but containing more mass than the Sun. Gravity has compressed matter to the point where a teaspoon of neutron star material would weigh billions of tons. The atoms are gone, crushed into a dense soup of neutrons. It's one of the most extreme forms of matter in the universe, held together by gravity's unrelenting squeeze. A city-sized ember, impossibly heavy, spinning in the dark. Jupiter protects Earth by deflecting asteroids. Jupiter, the giant of our solar system, plays a quiet but crucial role in Earth's safety. Its immense gravity acts like a cosmic shield, deflecting or capturing asteroids and comets that might otherwise threaten the inner planets. Some objects are flung out of the solar system entirely. Others are pulled into Jupiter itself, as happened spectacularly in 1994, when comet Shoemaker-Levy 9 broke apart and collided with a planet. Without Jupiter's gravitational influence, Earth would likely experience far more impacts. The giant planet doesn't protect us intentionally, of course. It's simply massive, and mass shapes the trajectories of everything nearby. In the slow dance of the solar system, Jupiter stands as a guardian, not by choice, but by presence, a quiet giant pulling danger away. Gravitational potential energy is what makes water flow downhill. When you lift an object, you're working against gravity, storing energy in the object's position. That stored energy is called gravitational potential energy. The higher you lift it, the more energy it holds. Release it, and gravity pulls it back down, converting potential energy into motion. This principle is everywhere. Water flows downhill because gravity pulls it from higher to lower elevations, releasing stored energy. Hydroelectric dams harness this, using falling water to spin turbines and generate electricity. A roller coaster climbs slowly to the top, storing energy, then releases it in a thrilling descent. Gravity doesn't just pull, it holds potential, waiting patiently for the moment when height becomes motion and stillness becomes speed. The faster you move, the less you weigh. This is one of relativity's strange truths. As you move faster, especially at speeds approaching the speed of light, your mass increases from the perspective of a stationary observer. But there's another effect. Your experience of gravity changes. Time dilation and length contraction alter how you interact with gravitational fields. If you were moving at relativistic speeds near a planet, you'd measure gravity differently than someone standing still. You'd also age more slowly. At everyday speeds, these effects are far too small to notice. But they're real. Motion and gravity are entwined, two aspects of the same curved space-time. The faster you go, the stranger the universe becomes, bending in ways that challenge intuition and rewrite the rules of weight, time, and distance. Gravitational binding energy holds planets together. Planets aren't held together by glue or structure. They're held together by gravity. Every particle in a planet pulls on every other particle, creating a gravitational binding energy that resists being pulled apart. For small objects like asteroids, this binding is weak. A strong enough impact can shatter them. But for planets, the binding energy is immense. To completely disassemble Earth, scattering every atom into space, would require more energy than the Sun produces in a week. Gravity doesn't just shape orbits, it holds worlds intact. It's the reason planets are round, why their cores are hot and compressed, and why they don't simply drift apart. Mass attracts mass, and in that attraction, planets find their form, solid, whole, and bound by invisible threads. Microgravity affects the human body in unexpected ways. In space, without gravity's constant pull, the human body begins to change. Bones lose density because they're no longer supporting weight. Muscles weaken, especially in the legs and back. Fluids shift upward, causing puffy faces and thinner legs. The heart doesn't have to work as hard. so it shrinks slightly. Even vision can be affected as pressure changes in the skull. Astronauts on long missions exercise for hours each day to counteract these effects, but the changes are inevitable. Gravity isn't just a force we experience. It's a force we're built for. Our bodies expect it, rely on it, and struggle without it. In microgravity, we adapt, but not without cost. We are creatures of weight, shaped by the pull of a planet. Gravitational redshift stretches light climbing out of a gravity well. Light doesn't just bend in a gravitational field, it also changes color. When light climbs out of a strong gravitational field, like escaping from near a massive star, it loses energy. This causes its wavelength to stretch, shifting toward the red end of the spectrum. The effect is called gravitational redshift. The stronger the gravity, the greater the shift. Light leaving the surface of a white dwarf, for example, is measurably redder than when it was emitted. Near a black hole, the redshift becomes extreme. Light struggles to escape, stretching so much it dims and fades. Time slows, light reddens, and even photons feel the weight of gravity's grip. Nothing escapes unchanged. Every mass tells space-time how to curve. John Wheeler, a physicist who worked closely with Einstein's theories, once summarized general relativity in a single sentence. Space-time tells matter how to move. Matter tells space-time how to curve. It's an elegant description of gravity's true nature. Your body, the chair, the earth, the sun. Every atom and every star bends the fabric of space-time around it. That curvature is what we experience as gravity. The more mass, the deeper the curve. The deeper the curve, the stronger the pull. There's no mysterious force reaching across space. There's only geometry, the shape of reality itself, molded by the presence of mass and energy. We don't fall because we're pulled. We fall because we're following the contours of a curved universe. Lagrange points are gravitational balance zones. In the dance between two massive objects, like the Earth and the Sun, there are special locations where their gravitational pulls balance perfectly with the centrifugal force of orbital motion. These are called Lagrange points, and there are 5 of them in every two-body system. At these points, a smaller object like a satellite can remain relatively stable without using much fuel. The James Webb Space Telescope, for example, sits at L2, a point beyond Earth's orbit where the gravity of the Sun and Earth work together to keep it in position. These zones are quiet refuges in space, places where forces cancel and objects can rest. Gravity doesn't just pull. It also, in rare places, creates stillness. Earth's gravity holds our atmosphere in place. Without gravity, Earth's atmosphere would drift away into space. Gas molecules move constantly, bouncing and vibrating. Some move fast enough to reach escape velocity, especially lighter gases like hydrogen and helium, which is why Earth has lost most of its primordial hydrogen over billions of years. But heavier molecules like nitrogen and oxygen are held close by gravity's pull. The atmosphere forms a thin shell around the planet, densest at the surface and thinning gradually with altitude. This protective blanket shields us from radiation, burns up meteors, and sustains life. Every breath you take is held here by gravity, a gift from the planet's mass. The air around you isn't just floating. It's being pulled gently downward, kept close, like everything else on this spinning world. The moon's gravity is 1/6 of Earth's when astronauts first stepped onto the moon in 1969. They moved with a strange, bouncing gait. It wasn't just excitement or the bulky spacesuits. It was gravity, or the relative lack of it. The moon's mass is much smaller than Earth's, and its gravity pulls with only about 1/6 the strength. A person who weighs 180 pounds on Earth would weigh just 30 pounds on the moon. This weaker pull is why astronauts could jump higher, despite their heavy equipment, and why dust kicked up by their boots arced so gracefully before settling back down. The moon's weak gravity also explains why it has no atmosphere. Gas molecules can easily reach escape velocity and drift away into space. On the moon, gravity whispers rather than speaks. And in that whisper, we feel how much Earth's strong embrace shapes everything we know. Gravity makes black holes invisible but detectable. A black hole emits no light, produces no sound, and cannot be seen directly, but its gravity gives it away. Astronomers detect black holes by watching how they affect nearby matter. Gas spiraling into a black hole heats up to millions of degrees, emitting X-rays before crossing the event horizon. Stars orbiting invisible companions reveal the presence of black holes through their motion. And when black holes merge, they send gravitational waves rippling through space-time. In 2019, scientists released the first image of a black hole's shadow, a dark circle surrounded by glowing gas. We don't see the black hole itself. We see the absence, the void where light cannot escape. Gravity makes black holes invisible, but paradoxically, it's also how we find them. Darkness outlined by light. Tidal forces can tear moons apart. Moons orbit planets, held in place by gravity. But if a moon ventures too close, tidal forces, the difference in gravitational pull across the moon's body, can become destructive. The side facing the planet feels a stronger pull than the far side. If the moon crosses a boundary called the Roche limit, these forces overcome the moon's own gravity, and it begins to break apart. The debris often forms a ring around the planet. Saturn's magnificent rings may have formed this way, from moons shattered long ago by tidal stress. Phobos, one of Mars' moons, is slowly spiraling inward and may one day meet the same fate. Gravity doesn't just hold things together. Sometimes, when the balance tips, it tears them apart. Beauty born from destruction, spinning silently in the dark. Gravitational waves carry information about colliding black holes. When two black holes spiral toward each other, their dance creates ripples in space-time that travel outward at the speed of light. These gravitational waves carry information about the collision, the masses of the black holes, their spin, the energy released, and even the shape of the final merged black hole. Detectors on Earth, like LIGO and Virgo, measure these waves by tracking tiny changes in the distance between mirrors, changes smaller than the width of a proton. Each detection is like hearing a cosmic event, a low rumble that rises in pitch and intensity before suddenly cutting off, the moment of merger. It's a new form of astronomy. Instead of seeing light, we feel vibrations in the structure of space itself. Gravity singing across the universe finally heard. The sun's gravity creates the solar wind shape. The sun doesn't just emit light. It also releases a constant stream of charged particles called the solar wind. This wind flows outward in all directions, but it doesn't travel in straight lines. The sun's gravity curves its path, and the sun's rotation causes it to spiral. Together, these effects create a structure called the Parker spiral. a graceful curve that extends throughout the solar system. Solar wind particles follow these invisible highways shaped by gravity and motion. When the wind reaches Earth, our planet's magnetic field deflects most of it, creating the auroras when some particles slip through. The solar wind is shaped not just by the sun's energy, but by its mass, by the curvature of space around it. Even wind bends to gravity's will. Gravitational collapse triggers supernova explosions. When a massive star runs out of fuel, its core collapses in less than a second. The implosion is so violent that it rebounds, sending a shock wave tearing through the star's outer layers. This rebound, powered by gravity's sudden catastrophic compression, creates a supernova. For a brief time, the dying star shined brighter than an entire galaxy. Elements forged in the core and in the explosion itself, carbon, oxygen, iron, gold, are scattered into space, seeding future generations of stars and planets. Supernovae are among the most energetic events in the universe, and they're triggered by gravity. Not a slow, patient pull, but a sudden, overwhelming collapse. In the end, even stars bow to gravity's final command, falling inward before bursting outward in one last brilliant gasp. You can orbit anything with mass. Orbit isn't limited to planets and moons. Any object with mass creates a gravitational field, and in theory, you can orbit it. Astronauts orbit Earth. Earth orbits the Sun. The Sun orbits the center of the Milky Way. But you could, in principle, orbit a mountain, a city, or even another person, if you could move fast enough and if there were no air resistance or other forces interfering. The smaller the mass, the slower the required orbital speed, and the closer you'd have to be. In practice, this becomes impossible for small objects because surface features and friction get in the way. But the principle holds. Gravity is universal. Every mass curves space-time around it, creating the possibility of orbit, a dance available to anything with weight and motion. The Milky Way's gravity holds hundreds of billions of stars. Our galaxy, the Milky Way, is a vast spiral structure containing somewhere between 200 and 400 billion stars. What keeps them together? Gravity. At the center lies a supermassive black hole, millions of times the mass of the Sun. But most of the galaxy's gravity comes from the combined mass of all its stars, gas, dust, and dark matter. Stars orbit the galactic center, some quickly, others slowly, depending on their distance. Our Sun takes about 230 million years to complete one orbit. The galaxy rotates, but not like a solid disk. Inner regions move faster than expected, and outer regions don't slow down as they should. This discrepancy suggests the presence of dark matter, invisible mass providing extra gravitational pull. The galaxy is held together by gravity, seen and unseen, binding light across 100,000 light years. Gravitational potential energy powers geysers. Beneath Yellowstone's surface, water seeps into chambers heated by volcanic rock. As the water heats, pressure builds. Eventually, the pressure overcomes gravity's hold on the column of water above, and the superheated water flashes to steam, erupting violently upward. This is a geyser, powered by heat, yes, but also by gravity. The weight of the water column keeps the system pressurized until the breaking point. When the eruption ends, water drains back down, pulled by gravity, and the cycle begins again. Old Faithful and countless other geysers around the world are reminders that gravity shapes not just orbits and tides, but also the dynamic forces within our planet. What goes up, pulled by pressure and heat, must come down, pulled by gravity's patient, inevitable hand. Gravitational acceleration on Earth is 9.8 meters per second squared. Drop an object, and it accelerates downward at approximately 9.8 meters per second squared. This means its speed increases by 9.8 meters per second for every second it falls, ignoring air resistance. After 1 second, it's falling at 9.8 meters per second. After 2 seconds, 19.6 meters per second. This rate is remarkably consistent across Earth's surface, though it varies slightly with altitude and location. It's often called little g, to distinguish it from the gravitational constant, big G, which describes the strength of gravity throughout the universe. This number, 9.8, is woven into the experience of life on Earth. It's why we can walk upright, why rain falls, why a thrown ball arcs downward. Gravity's rhythm, measured and constant, ticking through every moment. Stars orbit the galaxy at different speeds. In our solar system, planets farther from the Sun move more slowly in their orbits. Neptune crawls compared to speedy Mercury, but galaxies don't work that way. Observations show that stars in the outer regions of galaxies orbit at roughly the same speed as stars closer to the center. This is strange. According to Newton's laws, outer stars should move more slowly because they're farther from most of the galaxy's mass. The fact that they don't suggests there's extra mass we can't see, providing additional gravitational pull. This unseen mass is called dark matter, and it seems to form a vast halo around galaxies. We don't know what it's made of, but we know it's there because of how it affects motion. Gravity reveals what light cannot. Gravitational potential wells explain why planets are round. Small asteroids can be oddly shaped, lumpy and irregular, but planets are round. Why? Because gravity pulls equally in all directions. As a planet forms, material falls inward, drawn by the gravity of the growing mass. Over time, the stronger pull toward the center smooths out irregularities. Anything sticking up too high is pulled down. Anything too low is filled in. The result is a sphere, the shape that minimizes gravitational potential energy. Larger objects with stronger gravity become rounder. Smaller objects with weaker gravity can maintain irregular shapes because their internal strength resists the pull. Roundness isn't imposed. It's the natural result of gravity seeking balance. Planets are round because gravity doesn't favor any direction. It pulls toward the center, always, and the center of a sphere is everywhere equidistant from its surface. Gravitational time dilation affects particle decay. Certain subatomic particles are unstable and decay after a predictable amount of time, but that time depends on the observer's frame of reference. A particle moving at high speed or deep in a gravitational field will appear to decay more slowly to an outside observer. This isn't an illusion. Time genuinely passes more slowly in stronger gravity. Experiments with particles in accelerators confirm this. When particles are accelerated to near light speed, they live longer from our perspective than they would at rest. The same principle applies to gravity. Time is not a universal constant ticking the same for everyone, everywhere. It's flexible, influenced by speed and mass. Even the fleeting lives of particles are shaped by the curvature of space-time around them. Binary star systems orbit a shared center of mass. Many stars come in pairs, locked in gravitational embrace. These binary systems orbit not around each other, but around a point between them called the barycenter. If the stars have similar masses, the barycenter lies roughly midway. If one star is much more massive, the barycenter is closer to it, and the smaller star traces a larger orbit. Some binary stars are so close they exchange material, pulling gas from one another in swirling streams. Others are separated by vast distances, barely influencing each other. Binary stars are common in the universe, perhaps more common than single stars like our Sun. They're proof that gravity doesn't just create orbits, it creates partnerships, systems where two bodies dance together, bound by mutual pull, spinning endlessly through space. Gravitational waves stretch and squeeze space-time. When a gravitational wave passes through you, it doesn't push you or pull you in the traditional sense. It stretches and compresses the space around you. If a wave travels through your body vertically, you'd be stretched taller and squeezed narrower, then squeezed taller and stretched wider, oscillating back and forth. The effect is incredibly tiny, far too small to feel. LIGO detects changes in distance smaller than the width of a proton. But the principle is profound. Gravitational waves don't travel through space. They are distortions of space itself, ripples in the fabric of reality. Passing through us, mostly unnoticed, they're a reminder that space is not empty and static. It's dynamic, flexible, and alive with invisible motion. The Schwarzschild radius defines a black hole's event horizon. For any given mass, there's a radius at which, if you compress that mass enough, it will become a black hole. This is called the Schwarzschild radius. For Earth, it's about 9 millimeters. Compress the entire planet into a sphere smaller than a marble, and it would collapse into a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. The radius depends only on mass. The more massive the object, the larger the radius. At the Schwarzschild radius, space-time is so warped that the escape velocity equals the speed of light. This boundary is the event horizon, the point of no return. Inside, all paths lead inward. Gravity becomes absolute. The Schwarzschild radius is not a physical surface. It's a threshold in geometry where the rules change and the universe goes silent. You create gravitational waves when you move. Technically, any accelerating mass produces gravitational waves. That includes you. When you wave your hand, jump, or spin in a circle, you disturb space-time, creating tiny ripples. But the effect is absurdly small, far too weak to measure with any existing technology. Gravitational waves from everyday motions are lost in the noise of the universe. Only the most violent cosmic events, colliding black holes, merging neutron stars, supernovae, produce waves strong enough to detect across light years. Still, the principle stands. You are part of the gravitational conversation. Your motion matters. You disturb the fabric of space-time with every breath and step, leaving a wake too faint to measure but real nonetheless. Even in stillness, you shape the space around you. In motion, you make it ripple. Planets migrate due to gravitational interactions. Planets don't always stay where they formed. Gravitational interactions with other planets, asteroids, or the disk of gas and dust around a young star can cause planets to migrate inward or outward over millions of years. Jupiter, for instance, may have migrated inward early in the solar system's history before drifting back out, scattering smaller bodies in its wake. This process, called planetary migration, helps explain why we see hot Jupiters, massive planets orbiting extremely close to their stars in other solar systems. They likely formed farther out and spiraled inward due to interactions with the protoplanetary disk. Gravity doesn't just build solar systems, it rearranges them. Planets are not fixed in place. They wander, nudged by invisible forces, reshaping their homes over deep time. Gravitational redshift was confirmed by the Pound-Rebka experiment. In 1959, physicists Robert Pound and Glenn Rebka conducted a delicate experiment at Harvard. They sent gamma rays up a 22.5-meter tower and measured their frequency at the top. The photons, climbing against Earth's gravity, lost a tiny amount of energy, causing their wavelength to shift toward the red. The shift was minuscule, but detectable with precise instruments. This confirmed Einstein's prediction that gravity affects light and time. Even in a weak gravitational field like Earth's, over a short distance, the effect is real. Light doesn't just bend in gravity, it reddens as it climbs and blue shifts as it falls. The experiment was a triumph of precision, measuring something almost impossibly small and proving once again that gravity shapes everything, even the color of light. Gravity affects the flow of time on GPS satellites. Every smartphone with GPS relies on a network of satellites orbiting Earth at about 20,000 kilometers altitude. Up there, gravity is weaker, and time flows slightly faster than it does on the ground. The difference is small, about 38 microseconds per day, but if uncorrected, GPS coordinates would drift by several kilometers within a day. Engineers must account for both gravitational time dilation and the time dilation caused by the satellite's motion. Special and general relativity, once abstract theories, are now essential for everyday navigation. Your phone knows where you are because scientists understand how gravity warps time. Every time you check a map or navigate with GPS, you're using Einstein's equations, silently correcting for the subtle bend of space-time. Gravitational binding energy is released when stars form. When a cloud of gas collapses to form a star, gravitational potential energy is converted into heat. As particles fall inward, they speed up, colliding and generating thermal energy. This heating is what eventually ignites nuclear fusion in the star's core. But even before fusion begins, the collapsing gas glows, radiating energy into space. This is called a protostar. For millions of years, a protostar shines purely from gravitational contraction, growing hotter and denser until the core reaches the temperatures needed for hydrogen fusion. Gravity doesn't just crush matter, it releases energy in the process. Every star begins its life glowing with the warmth of collapse, a fire kindled not by chemistry or fusion, but by the simple, patient pull of mass toward mass. Black holes can spin at incredible speeds. Black holes aren't just massive. Many of them spin. When a rotating star collapses into a black hole, it carries its angular momentum with it. As the core shrinks, it spins faster, like a figure skater pulling in their arms. Some black holes rotate at nearly the maximum possible rate, close to the speed of light at their event horizon. This rotation drags space-time around with it, an effect called frame dragging. Near a spinning black hole, even if you tried to remain still, you'd be pulled along with the swirling space-time. The faster the spin, the more dramatic the effect. Spinning black holes are among the most dynamic objects in the universe, warping not just space, but time and motion, pulling the very fabric of reality into a whirlpool. The equivalence principle links gravity and acceleration. Einstein's equivalence principle states that the effects of gravity are locally indistinguishable from acceleration. If you're in a closed room with no windows, you can't tell whether you're standing on Earth, feeling its gravity, or accelerating upward in a spaceship at 9.8 meters per second squared. Both feel the same. This insight was the seed of general relativity. It means gravity isn't a force in the traditional sense. It's the experience of curved space-time. When you stand on Earth, you're not being pulled down. You're trying to follow a straight path through curved space-time. And the ground is accelerating up to meet you from the perspective of space-time itself. It's a shift in perspective that changes everything. Gravity and acceleration are two sides of the same coin, unified in the geometry of the universe. Gravitational potential energy is why dams generate power. Water held behind a dam sits high above the turbines below. That elevation gives the water gravitational potential energy. When gates open and water flows downward, gravity converts that potential energy into kinetic energy, the energy of motion. The rushing water spins turbines, which generate electricity. The higher the dam, the more energy each kilogram of water can release. Hydroelectric power is, in essence, harvested gravity. The same principle applies to pumped storage facilities, which pump water uphill when electricity is cheap and release it downhill when demand is high. Gravity becomes a battery, storing energy in height and releasing it in flow. Silent, patient, and endlessly renewable, gravity powers rivers and cities alike. The universe expands, but gravity resists. On the larger scales, the universe is expanding. Galaxies are moving away from each other as space itself stretches. But gravity fights this expansion. It pulls galaxies together, forming clusters and superclusters. Within these structures, gravity dominates, holding galaxies in place even as the space between clusters grows. For billions of years, gravity slowed the expansion, though it never stopped it. Then, something changed. The expansion began accelerating, driven by a mysterious force we call dark energy. Now, the universe is not just expanding, but doing so faster and faster. Gravity still pulls, still binds galaxies and stars, but on cosmic scales, it's losing the battle. The universe is stretching, and gravity, strong as it is, cannot hold everything together. Gravitational microlensing reveals distant planets. When a star passes in front of a more distant star from our perspective, its gravity acts as a lens, briefly magnifying the background star's light. If the foreground star has a planet, the planet's gravity causes an additional blip in the light curve. This technique, called gravitational microlensing, has revealed planets thousands of light years away, many in orbits or environments that other detection methods can't reach. The alignment must be perfect and the effect is brief, often lasting only hours or days. Most microlensing events are one-time occurrences, never to be repeated. But in that fleeting moment, gravity reveals a distant world, a shadow cast in light, a reminder that even planets too far and faint to see can still bend space and announce their presence. Falling objects follow geodesics. In general relativity, objects in free fall aren't being pulled by a force. They're following the straightest possible path through curved space-time, a path called a geodesic. It's like rolling a marble on a curved surface. The marble doesn't swerve because something pushes it. It follows the shape of the surface. When you drop a ball, it's not falling because Earth pulls it. It's following the curvature of space-time created by Earth's mass. From the ball's perspective, it's moving in a straight line. From ours, constrained by the surface, it looks like falling. This shift in perspective is profound. Gravity isn't a force. It's the geometry of the universe. And every falling object traces a path written into the shape of space itself. Gravitational shielding is impossible. Unlike electromagnetic fields, which can be blocked with conductive materials, gravity cannot be shielded. There's no material you can place between two objects to reduce or eliminate the gravitational force between them. Gravity reaches through everything: walls, planets, even black holes. You can't hide from gravity. You can only move farther away, where the pull weakens with distance. This universality is both profound and humbling. Gravity connects everything all the time. There's no escape, no barrier, no refuge. Every atom in the universe pulls on every other atom. It's the one force that cannot be blocked, avoided, or turned off. In this sense, gravity is the most fundamental connection in existence, invisible but unbreakable. Tidal locking causes the moon to show one face. The moon always shows the same face to Earth. This isn't coincidence. It's the result of tidal locking, a gravitational process. Early in the moon's history, Earth's gravity created bulges in the moon shape. As the moon rotated, these bulges tried to stay aligned with Earth, creating friction that gradually slowed the moon's rotation. Eventually, the moon's rotation period matched its orbital period, about 27.3 days. Now, it rotates once for every orbit, keeping one side always facing Earth. Many moons in the solar system are tidally locked to their planets. Earth itself is slowly becoming tidally locked to the moon. Though this process will take billions of years, gravity doesn't just hold objects in orbit. Over time, it synchronizes their motion, turning rotation into stillness. Gravitational collapse can be halted by quantum pressure. Not all collapsing objects become black holes. If a star is too small, electron degeneracy pressure stops the collapse, creating a white dwarf. This pressure comes from quantum mechanics, specifically the Pauli exclusion principle, which prevents electrons from occupying the same state. Electrons resist being squeezed too close together, providing outward pressure. For more massive remnants, even electron pressure isn't enough, and neutrons take over, creating neutron stars supported by neutron degeneracy pressure. But if the mass is too great, not even quantum forces can resist gravity. The collapse continues, and a black hole forms. Gravity presses inward, quantum mechanics pushes outward. The final fate of a star depends on which force wins. In the end, gravity usually does. Your weight fluctuates slightly throughout the day. Earth's gravity isn't perfectly constant. It's affected by tides from the moon and sun, which slightly distort Earth's shape. These tidal forces make you very marginally heavier or lighter, depending on the time of day and the positions of the moon and sun. The effect is incredibly small, far too subtle to feel or measure on a bathroom scale. But with precise instruments, it's detectable. You're also affected by your latitude, altitude, and the density of rock beneath you. Local variations in gravity exist everywhere, influenced by mountains, valleys, underground cavities, and even ocean tides. The pull you feel right now is unique to this moment and this place. A gravitational fingerprint written in mass, distance, and time. Gravitational slingshots have sent probes beyond the solar system. The Voyager spacecraft, launched in the 1970s, are now in interstellar space, farther from Earth than any human-made object. They got there without carrying enormous fuel reserves. Instead, they use gravity assists, swinging past Jupiter and Saturn, stealing a bit of each planet's orbital energy to accelerate. Each encounter flung the spacecraft onward, faster and farther than rockets alone could achieve. Voyager 1 is now over 24 billion kilometers away and still sending faint signals back to Earth. Gravity, harnessed with precision, transformed an ambitious mission into a journey beyond the sun's reach. The planets, in a sense, gave a push, lending their momentum to a fragile craft carrying the hopes and curiosity of an entire species. The sun will eventually become a white dwarf, held up by quantum pressure. In about 5 billion years, the sun will exhaust its hydrogen fuel. It will swell into a red giant, shedding its outer layers into space. What remains will collapse under gravity until electron degeneracy pressure stops the contraction. The result will be a white dwarf, a dense, Earth-sized ember containing most of the sun's mass. No fusion will occur. The white dwarf will simply radiate its stored heat into space, cooling slowly over trillions of years. Gravity will hold it together. Quantum mechanics will hold it up. The sun's story will end not with drama, but with a long, quiet fade. A cooling cinder drifting in the dark, held in balance by forces both vast and invisible, ancient and patient as time itself. Gravitational waves can pass through anything. Unlike light or sound, gravitational waves don't interact with matter in the traditional sense. They pass through planets, stars, and even black holes without being absorbed or scattered. This makes them incredibly difficult to detect, but also incredibly valuable. Gravitational waves carry information from events that produce no light, like the collision of black holes. They arrive unaltered, a pristine signal from the distant universe. While electromagnetic waves can be blocked, absorbed, or distorted, gravitational waves are transparent messengers. They reach us from the earliest moments of cosmic history, from the densest cores of collapsing stars, from places light can never escape. In this transparency lies their power. Gravity speaks, and nothing in the universe can silence it. The Earth's core is compressed by gravity into a solid sphere. At the center of the Earth, about 6,000 kilometers below your feet, lies a solid ball of iron and nickel. You might expect the core to be molten given the intense heat, hot enough to melt metal. And indeed, the outer core is liquid, but the inner core, despite being even hotter, is solid. Why? Pressure. The weight of the entire planet pressing inward is so immense that it forces atoms into a solid crystalline structure, even at temperatures exceeding 5,000 degrees Celsius. Gravity doesn't just pull, it compresses. At Earth's core, the pressure is about 3.6 million times atmospheric pressure at sea level, enough to change the state of matter. Enough to turn molten iron into a solid sphere, spinning slowly in the dark, held together by the weight of the world above. Gravitational waves were first indirectly detected through binary pulsars. In 1974, astronomers discovered a binary system containing two neutron stars, one of which was a pulsar emitting regular radio pulses. By timing these pulses precisely, they could track the orbit of the system. Over the years, the orbit decayed. the two stars spiraled closer together, exactly as predicted if they were losing energy to gravitational waves. This indirect detection earned the 1993 Nobel Prize and confirmed that gravitational waves exist, decades before LIGO directly detected them. The binary pulsar system is still there, still spiraling inward, still radiating invisible waves into space. One day, millions of years from now, the two neutron stars will merge, and when they do, they'll send a final burst of gravitational waves echoing across the universe, a whisper from the end of a long, slow fall. Gravity creates the Roche limit for orbiting bodies. Every planet has a boundary, an invisible line called the Roche limit. Inside this limit, tidal forces from the planet are stronger than the gravitational forces holding a moon or asteroid together. If an object crosses the Roche limit, it begins to break apart, torn into fragments by the difference in gravitational pull across its body. Saturn's rings likely formed this way. A moon ventured too close and was shredded. The fragments now orbit the planet in beautiful, glittering bands. Comets that pass too close to planets can also be torn apart, as comet Shoemaker-Levy 9 was before it collided with Jupiter. The Roche limit is a boundary of survival. Inside, gravity destroys. Outside, gravity holds together, a line drawn by force and distance, subtle but absolute. Every breath you take is influenced by gravity. When you inhale, your diaphragm contracts and moves downward, expanding your lungs. Air flows in because of the pressure difference, but gravity also plays a role. In your lungs, gravity pulls blood downward, meaning the lower parts of your lungs receive more blood flow than the upper parts when you're upright. This affects oxygen exchange. In microgravity, fluids distribute differently, and astronauts' breathing changes. Their lungs work more evenly, but they also experience congestion as fluids shift toward the head. On Earth, every breath is shaped by the planet's pull, drawing air into your lungs and pulling blood through your vessels. Even this simple act, breathing in and out, is a dance with gravity. Silent, constant, essential. Gravitational lensing can create Einstein rings. When a massive object like a galaxy sits perfectly between us and a more distant light source, the light bends around the foreground object in all directions. If the alignment is just right, the distant source appears as a ring of light surrounding the closer object. These are called Einstein rings, and they're among the most beautiful phenomena in astronomy. They're rare, requiring precise alignment across billions of light years. The ring isn't a physical structure. It's an illusion created by warped space-time. Light from a single distant galaxy, split and bent by gravity, arrives at our telescopes from multiple directions, forming a perfect circle. It's a cosmic mirage, a reminder that even light must follow the curves of the universe. The more mass an object has, the slower time passes near it. Near the surface of Earth, time flows at a certain rate. Near the surface of a neutron star, time slows dramatically compared to a distant observer. Near the event horizon of a black hole, time nearly stops. This relationship between mass and time is not an illusion or a trick. It's a fundamental feature of space-time. Gravity warps not only space, but also the passage of time itself. Clocks tick slower in stronger gravitational fields. Processes age more slowly. Even decay rates are affected. This means that time is not universal. It's local, personal, shaped by where you are and what's nearby. The universe doesn't have a single clock. It has countless clocks, all running at different speeds, their rhythms determined by the mass around them. Falling feels like floating. When you're in free fall, you don't feel heavy. You don't feel the pull of gravity at all. You feel weightless. Astronauts orbiting Earth, skydivers before their parachutes open, passengers on a plummeting roller coaster, they all experience this strange lightness. It's not because gravity has disappeared. It's because everything is falling together. There's no force pushing back, no surface resisting the fall, so there's no sensation of weight. Free fall is the most natural state in a gravitational field. It's when you're standing still, held up by the ground, that you feel the force. In free fall, you're simply following the shape of space-time, and in that surrender, for a moment, you float. Gravity holds together the universe's largest structures. On the grandest scales, gravity is the architect of everything. Galaxies cluster together in groups and superclusters, bound by mutual gravitational pull. These clusters form along vast filaments of dark matter, stretching across hundreds of millions of light years, creating a cosmic web. Between the filaments lie voids, enormous empty regions with very few galaxies. This structure, called the large-scale structure of the universe, is shaped entirely by gravity. It's the result of billions of years of mass-attracted mass, small differences in density growing into immense concentrations of matter. Gravity writes the story of the universe in clusters and voids, in light and darkness, in structures so vast they're hard to imagine. And yet, it's all held together by the same gentle pull that keeps your feet on the ground. And now, we've come to the end of our gentle fall through the universe, through the quiet, invisible force that holds stars, planets, and even time itself. Gravity is always with you, pulling softly, shaping the path of light and the rhythm of your breath. It connects the smallest stone to the furthest galaxy, the present moment to the beginning of time. You've traveled far tonight, through black holes and binary stars, through collapsing cores and bending light, through the slow drift of moons and the silent ripples in space-time itself. And in all of it, there's been one constant, the pull, not harsh, not loud, but ever-present. Gravity as patient as the turning of planets, gravity as old as the universe. So now, let your body rest completely. Let your thoughts slow and soften. Let gravity hold you, the way it holds everything, gently and without effort. You don't need to resist. You don't need to move. Just let yourself be held. The ground beneath you, the air around you, the pull of the earth, all of it is here to support you. Sleep well, and may your dreams be as deep and quiet as the curve of space-time itself. Thank you for drifting here with us tonight. If this brought you peace, consider subscribing. There's always more to explore, one sleepy fact at a time. Good night.